Yeah, I guess I still wonder. One way to read a section of text like this is just to have a kind of, as it were, an image that flashes in my head whenever recursion is happening, and then to successfully have that image flash in my head. It's like, okay, this is recursion. It always looks the same. I don't need to look at the details. Uh, this seems like a more involved version of recursion. Hopefully, this is not actually how the system performs addition. Hmm. this, I think we have to be wary of. The form of this sentence suggests that this is like a search term, as it were, a term that's interconnected, as it were, via citations, via links to other a high impact word, as it were, in terms of journal impact, journal article impact rating. Whereas it might be that the interlocutor will construct sentences that it's like, given how this sentence is constructed, this must be a high impact word, or else the sentence is misconstructed. Maybe. And then that would suggest that this is a sort of a traded term where people use this as a shorthand for referring to a discourse. But then this might be exactly that. So. Whoa, 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 whoa. Let's slow down. I'm now, I now have, I've somehow coaxed the interlocutor to using a word that's sort of one step removed from crypto. Uh-oh. And now I'm saying the word. Oh no. Yeah, I think what my I don't know if I want to like have an official stance on this kind of question, but what strikes me to say at the moment is that there were a lot of interesting ideas in Vine or in Ethereum years and years ago. I kind of got buried under the mining craze and all of the fraud. Anyway. which is where this term comes from. So far as I know, distributed autonomous organization. Yes, well, the idea is that I want to have an idea, and then I want to just let it go and have it. I don't want to profit by it outside of reputation and maybe donations. Though I would like to keep having ideas. Okay. As opposed to a centralized bureaucratic organization where I would have to manage it. Oh, now we're 0 words away. Uh, so this is an interesting phrasing. Just as in most languages, types in Lean can take arguments. For instance, the type list nat describes lists of natural numbers. List string describes lists of strings. This is accounting for, and maybe this is how we should think about it as well. Plausibly it is. Where when I say list of nats, that's giving an argument to a type. That's not how I would think about it, because I think of giving arguments to functions where functions transform arguments. I don't think of this as a transformation of an argument. Again, maybe I should. Yes, the term polymorphism will refer to data types and definitions that take types as arguments. Okay. These type arguments can be used in the data type or definition, which allows the same data type or definition to be used with any type that results from replacing the argument's names as some other types. Which allows the same data type or definition to be used with any type that results from replacing the argument's names with some other types. Got some distractions floating around in my head. I'll do a different color scheme. I mean, maybe actually. let's do a little bit of light mode. I feel like the dark mode is just not working with my eyes at the moment. Alright, let's see. Just as a function definition's arguments are written immediately after the name being defined, a structure's arguments are written immediately after the structure's name. It is customary to use Greek letters to name type arguments in Lean when no more specific name suggests itself. Okay. For default type. Type is a type that describes other types, so nat, list, string, p.end all have type. Just like list, p-point can be used by providing a specific type as its argument. Okay, so similarly, if I said def list nat is equal to not a problem. Okay. feel like there's not a lot of in between. Maybe there's a good reason for that, I don't know. It's like it has to be black or blindingly bright. Well, no, obviously there are these distinctions between. No, that's interesting. That could work. Now that it lacks some of the coloring, doesn't it? It's just hard to tell the color distinction. Okay. I'd have to install it. Well, it has 2 million installs. That seems kind of trustable, sure. Okay, but then that's not what I just hit. Perusing themes instead of studying naturally. Yeah, one moment. Okay. Alright, good enough. Alright. For now, let's see. Okay, so why is this producing specifically 3 or -3? I don't understand that. Oh, because it's the because the function is positive or negative 3. Right. So this matching is not doing what I'm thinking it's doing. What is this doing? Yeah, it's difficult to reconcile this with my current formatting rules. What do I mean? So this everything prior to the equality sign is let's see, maybe we'd want to do like that. And that raises the question of whether I want this. Okay, and then we could move this up here. Yeah, some indication other than the colon, some sort of structural, some sort of formatting indication that some sort of formatting indication that this is the input and this is the output. Would be appreciated, but I'm not sure what that should be. I mean, if we did like this. Maybe. Okay. Because types are. Oh, what time is it? Yeah, my studying is not as efficient as it could be. Yeah. Because types are first class and can be computed using the ordinary rules of the Lean language. They can be computed by pattern matching against a data type. When Lean is checking this function, it uses the fact that the match expression in the function's body corresponds to the match expression in the type. To make nat to be the expected type for the pos case and to make int to be the expected type for the neg case. It's a long sentence. When Lean is checking this function, it uses the fact that the match expression in the function's body corresponds to the match expression in the type. So, according to that terminology, this is the type or this is the type, which I guess the whole thing being the type makes sense. Applying pos or neg3 to sign pos results in the argument name s. Wait, what is this telling me though then? To make nat be the expected type for the positive case and make int be the expected type for the neg case. Alright. Applying pos or neg3 to sign pos results in the argument name s. Both the body of the function and its return type being replaced by sign pos. where in this case S is sine. Right, because the argument would be I think I'm not quite reconciling that this is pattern matching in the same way that all of our other uses of pattern matching have been pattern matching. Well, and that would be because when we've been using pattern matching, e.g. on the lists, null and then head tail are more obviously structural. It's like if I input sine pos, that's merely the value of S, or sine neg. It's merely the value of S. Whereas, well, so null would also be the value of a list. To the extent that head colon colon tail designates car, like const car of the list onto CDR of the list, that also designates the list. Strange to me that this would be called pattern matching. This is of the same kind of, that this is the same thing that you're doing with pattern matching as in the other case. Applying pos or neg3 to sine pos results in the argument name S in both the body of the function and its return type being replaced by sine pos. Evaluation can occur both in the expression and its type. Match sine pos with sine pos. And linked lists. Lean's standard library includes a canonical linked list type called list, with special syntax that makes it more convenient to use. Lists are written in square brackets. For instance, a list that contains the prime numbers less than 10 can be written def primes under 10 list nat. Okay, makes sense. Behind the scenes, list is an inductive data type defined like this. Check chat in a while. What are you up to, chat? What game am I developing? Fun with words. I have no time for games. Yeah, so as we've already discussed with the interlocutor over here, let me see. I had to find it. Right, so if I want a list with mixed types, we have to have e.g. here value. So inductive is a way of designating a sum type. Okay, and in this case, the cases for the sum type are nat, bool, and string. Okay, now I can have a list of values, and then that will allow me to mix nats, bools, and strings into a list together. This sort of intermediate requirement is strange and confusing to me, but we'll ignore that. Okay. Coming from Lisp, where I can put whatever I want into lists, this restriction is chafing. According to the constructors, list alpha can be built with either nil or const. This usage of the word constructor is still it's still strange, but it's making more sense. I mean, what was particularly strange, the discussion about plus addition discussion. So these match forms are always going to destructure the term, as the interlocutor calls it, which in this case means that let's see. So our k term, our k value, is replaced by the natural successor of k prime. So then we have natural successor plus in k prime. Okay. Now what is the idea? So natural successor of k prime is the value of k, which merely tells me that k prime is 1 less than k. Well, that's not all it tells me, though. The point is that pattern matching wants to express our k term with either of its two possible states. It's either 0 or it's the successor of some other number. Yeah, it's just, it seems like some kind of unnecessary, some needless shuffling around to have particularly this out here, the natural successor of plus in k prime. It's like, why are we shuffling this natural successor out front? Okay, but the point is we have to have k prime for pattern matching purposes, and then as it turns out, given the properties of natural numbers, if I add in and k prime, that's going to be 1 less than k plus n. I'm not sure I'm making a useful point there. Let's go back. Also, quick question, how does this color theme work with, oh, look at that. I like that. Okay, let's see. The only complaint I really have about this color theme, maybe there could be more color distinction between these two. And maybe you could have a little bit darker gray in the background. But otherwise, we'll play around with this. Anyway, so we're talking about lists, right? So list takes a single type as its argument because you can only have homogeneous lists. This type is the type of entry stored in the list. According to the constructors, a list alpha can be built with either nil or cons. The constructor nil represents empty lists, and the constructor cons is used for non-empty lists. The first argument to cons is the head of the list. So saying cons is a constructor for lists, it has some sort of semantic friction with Racket, where semantic friction with Racket. What do I mean? So if I have cons 1, 2, this does not create a list. Shouldn't anyway. Yeah, no, false. Not a list. Rather, it is a pair. Okay. Now, you can make a list using cons by doing cons 1 null. Okay. But now we're saying const is a constructor for a list. Well, it is one of the few ways of creating a list, in Racket at least. According to the constructors, namely nil as a constructor and const as a constructor, a list of alphas can be built with either nil or const. And then that's also a strange... List alpha can be built with nil. It's just a different way of talking. Well, and the point would be, yeah, if you start with nil, it's still a list of type list alpha. Okay, so you could not take nil and then proceed to cons on elements of type beta instead. Okay. The constructor nil represents empty lists, and the constructor const is used for non-empty lists. So similarly to the successor of k prime, const is a constructor for lists of the form const head to tail. The first argument to const is the head of the list. The second argument is its tail. A list that contains n entries contains n const constructors, the last of which has nil as its tail. Okay. So it has n plus 1 constructors for lists, n of which are const and one of which is nil at the end. The primes under 10 example can be written more explicitly using lists constructors directly. So list const 2 onto list const 3 onto dot dot dot. And we could also do, I think, def primes under 10. I will make that 2, 3, 5, 7. Apparently that is not a suitable way of doing this. Oh. There we go. It works. Let's throw in another number in there as a treat. Alright, so we don't have to use list const if we don't want to. We can use the double colon. You'd think they would give us that kind of option in Racket where we have to write consts hundreds of times per program, but whatever. These two definitions are completely equivalent, but primes under 10 is much easier to read than explicit primes under 10. And you just use the brackets, fine. Right, functions that consume lists can be defined in much the same way as functions that consume nats. Where consume here is a verb that effectively means well, yeah, you have to come up with some kind of semantics that incorporates the word consume. I don't think about decrementing a counter as consuming natural numbers, but I could. Indeed, one way to think of a linked list is as a nat that has an extra data field dangling off each successor constructor. Huh. That is not a way of thinking about lists that Lisp has encouraged me to deploy. One way to think of a linked list is as a nat that has an extra data field dangling off each successor constructor, which would be the data field that holds the entry in that position in the list. And the point would merely be that there is some natural number corresponding to each position in the list. Or more to the point, starting at 0 and then counting upward for each such natural number, there is some corresponding position in a list that has the same length as the natural number indexed to 0. From this point of view, computing the length of a list is the process of replacing each const with a successor and the final nil with a 0. Just as replace x took the type of the fields as the point of, just as replace x from earlier, where we replaced the x coordinate of a Cartesian pair, just as replace x took the type of the fields of the point as an argument, length takes the type of the list's entries. Okay. For example, if the list contains strings, then the first argument is string this is confusing me, hold on. First argument is string length string. Why can't I do though that doesn't fix it. Interesting. Yeah, I think you're supposed to type list.length. Yeah, this defines length. Sometimes I don't want to get back into the habit of complaining about the books we read, but this author's writing style is a little bit confusing. Like, length would naturally be, length reasonably would be a primitive operator that returns length, like a primitive polymorphic operator for finding the lengths of various primitive data objects. But it's not. It's but then furthermore, if it's not a primitive operator, and then strangely we're presenting it as if it is a primitive operator, you'd think the definition would come first, but instead the definition comes after. It's actually the same thing in the same author wrote the Little Typer, and that this kind of habit appears in the Little Typer as well, so far as I've read, where before presenting the definition of a function, the author insists that this is so in the Little Typer, the same author says which nat as a definition, and then it's target, base, and step with much more legible formatting here in Dr. Racket. Right, and now without specifying, well, so the way which nat works in the Little Typer is that we have which nat, target, base, step, and cond. Well, actually, it could be an if 0 target, then return base, otherwise return step of target. Actually, step of sub 1 target. Yeah, but so the author presents just this without the definition, and now I'm supposed to infer that step means step down. Well, no, it doesn't end up meaning, it doesn't have to mean step down. I'm not explaining this so effectively. I'm saying that the author presents information in a curious and befuddling way, where this definition is presented and then talked about as if I already know how it works, and then only afterward is an instance of its use presented. Whereas it's not clear at all what that step means. We're going to do something with the input. Anyway, here, length, which could be a primitive operator, but it turns out it isn't. Or even if it is, this isn't the primitive operator. As in, list.length might be a primitive operator, but this is not. Now, this is presented with no commentary on whether it's primitive or not. Turns out it isn't. Let's see. From this point of view, computing the length of a list is the process of replacing each const with a successor and the final nil with a 0, just as replace x took the type of the fields of the point as an argument. Length takes the type of the list's entries. For example, if the list contains strings, then the first argument is string. Yeah, but why would that be the case? I mean, I think actually the primitive is list dot, and then in that case, yes, which makes this even stranger. If you use the primitive argument list dot length, you don't have to supply the type of this. If I instead had list A and then list B, that also doesn't require a specification of the type of the element that's in the list. So it's not the case that the actual primitive length argument takes the type of the list's entries, making this all the more confusing. For example, if the list contains strings, then the first argument is string. Okay, so it's out of nowhere. This at the same time introduces that we're going to be working with a new definition that the author presents, does not say that this is going to be defined by the author, and then describes this in a way where you can't describe the primitive operator of length in the same way. Strange. Anyway. So this is describing a process whereby we programmatically replace instances of list const with natural successor. Okay. Alright, it's probably about time to take a break. What time is it? Yep. Alright, I gotta stand up. Going on these long tirades against the author, as I have a bad habit of doing, takes time. Alright, step away. Be right back. Okay, one moment. focusing on Lean as a programming language first, because I surmise that this will eliminate much needless tedium in interacting with the theorem prover. When we get around to proving theorems, I don't want to have to keep checking references just to figure out how the syntax works. Whether that requires me to read an entire book on functional programming, well, might as well double up here. One of my favorite things is getting double credit. My favorite thing. A scant 7.5 more minutes. So this successively replaces this is describing a recursive function naturally. Okay. Definition of length is both polymorphic because it takes the list entry type as an argument. Though why does it need to do that, I wonder? Why do you suppose it needs the argument type in this case? Let's see. Yeah, why doesn't this definition work? I mean, maybe it does, but why wouldn't we just use yeah, that works fine. Though, maybe that's the automatically inserted. Implicit parameter. Hey, look, implicit arguments. Did I just scroll over this? Hold on. So indeed, in most languages, the compiler is perfectly capable of determining type arguments on its own, and it only occasionally needs help from users. This is also the case in Lean. Arguments can be declared implicit. by wrapping them in curly braces instead of arguments when defining a function. For example, a version of replace x with an implicit type argument looks like this. A structure update of an existing value can be given via with colon curly brace point with x is assigned to 1. Interesting. Okay, fine. More built-in data types. In addition to lists, Lean's standard library contains a number of other structures and inductive data types that can be used in a variety of contexts. Option. Not every list has a first entry. Some lists are empty. Many operations on collections may fail to find what they are looking for. For instance, a function that finds the first entry in a list may not find any such entry. It must therefore have a way to signal that there was no first entry. Many languages have a null value that represents the absence of a value. Instead of equipping existing types with a special null value, Lean provides a data type called option that equips some other type with an indicator for missing value. For instance, a nullable int is represented by option int, and a nullable list of strings is represented by the type option list string. Introducing a new type to represent nullability means that the type system ensures that checks for null cannot be forgotten, because an option int can't be used in a context where an int is expected. Means that the type system ensures that checks for null cannot be forgotten. I'm not getting this sentence. Let me think here. We're going to ask for help on this sentence. Let's see. For now, we keep reading functional. These the author is saying. Let's see. So it's Lean's type system standing up and saying, "I will not let you forget to account for absence." Okay. What the author is saying: a nullable int is represented by option int. In Lean, as in Haskell or Rust, a value that might be missing is represented by an option type. Option int has two cases: some in, where in is an int, and none, which means no value present. This is how Lean represents what other languages, like Java, Python, and Racket, call null. What does checks for null cannot be forgotten mean? In many other languages, e.g. Java, int x equals maybe int. Maybe int might be null, crash at runtime. If you forget to check for null, the program crashes, or worse, misbehaves subtly. But in Lean, the type system won't let you treat an option int as an int. Lean will reject this with a type error because you haven't unwrapped the option. You're forced to handle the none case before you can get at the end. Yeah, so I guess my confusion here. So I would have to choose to use option int instead of int. And then the system will force me to remember that int could be, on some occasions, a null. So but seemingly then the use of option is going to be option is going to allow me to default outputs to null. So if I say, if something unexpected happens, produce a null. And then I say, this value is either int or null. But then what I mean by that, or a shorthand for that is saying option int. Maybe that's the idea. Let's see. Oh, I'm cleaning my glasses. One moment. All right, let's see. In languages like Racket or Python, whether a value can be null is a matter of convention or runtime awareness. In Lean, it's a matter of type. And so it's tracked everywhere automatically. Um, This makes all the following impossible: forgetting to check, passing a nullable value into a non-nullable context, crashing on dereference. Alright. Hold off on that. What time is it? Okay, let's see. Option has two constructors called sum and none constructors, notably, that respectively represent the non-null and null versions of the underlying type. The non-null constructor sum contains the underlying value, while none takes no arguments. The option type is very similar to nullable types in languages like C# and Kotlin, but it is not identical. In these languages, if a type, say Boolean, always refers to actual types, if a type, say Boolean, always refers to actual values of the type, true and false, values of the type, paren, true and false, paren, the type of Boolean ? Or nullable Boolean additionally admits the null value. Tracking this in the type system is very useful. The type checker. So tracking this in the type system instead of elsewhere. Tracking in the code, I guess. The type checker and other tooling can help programmers remember to check for null. And APIs that explicitly describe nullability through type signatures are more informative than ones that don't. However, these nullable types differ from Lean's option in one very important way, which is that they don't allow multiple layers of optionality. Option int can be constructed. This option int might be a null instead. Right, so underscore in patterns underscores match anything at all, but do not introduce variables to refer to the match data. So let's see if we can, guess, cap off this segment. Let's solve a leak code problem in lean and easy. Yeah. I'm still doing easies in racket. Maybe I shouldn't be, but I am doing easies in racket, so... we did shuffle the array. Running sum of a one-dimensional array sounds roughly our level at lean. Let's see what this is. Okay, so seemingly here we want to reverse the input list. And now there can't be a discount for 3, so we deposit 3. And then we look for a value that is greater than 3. Well, no, if the value is less than 3, then we put that value into the comparison slot. If it's greater than 3, it's a little bit more complicated, isn't it? Well, if it's greater than 3, then you receive the discount. Actually, it might be greater than or equal to. Yeah, it's greater than or equal to. Alright. If it's greater than or equal to 3, you receive the discount, and then we replace 3 with some new value. Well, it'd be this, the 2. Okay, but let me think here. So the problem with our naive approach that initially came to mind is that, this is problem 1475 if you're keeping score here. So we cycle through 3, then 2. Let's say this was 3 and then 5. And then this was 4. Okay, so let me get that over into racket actually. My note taking ID. Alright, so we're gonna 3, 2, 6, 4, 8. Alright, and now we're gonna replace this with a 5, this with a 4. Alright, so now cycling forward, we have 3 to 5, so 3 doesn't receive a discount. And then we have 5, which does receive the 3 discount, so 2, 3. And now 4 receives the discount of 3 as well. Okay, so we can't simply drop for the next number. Yeah, that complicates matters, doesn't it? This actually sounds like a job for a heap. We could keep the min and the max values we've encountered. Well, it seems like we have to keep all of these values because we couldn't... I mean, we wouldn't need to keep duplicates, and there are some other restrictions on what we have to keep, but we could run into a number that's only satisfied by a number much deeper into the list, like 8. Well, no, actually, it would be a smaller number. It'd be like if we had... we want gaps in numbers, I guess, like 4, 6, 8, and then either 5 or 7 as an example. Get rid of the 1, it's not serving any point in this example. Now 5 has to look all the way over to 4, 7 has to look all the way over to 6. Well, no, actually 7 would look at 5. Which suggests some kind of mathematization. Like whatever satisfies 5, in this case 4, is also going to satisfy any larger number. But then in this case we need 6 instead of 4. Huh. So hence a heap, where I could run heap remove min, or I could run heap min repeatedly until I found the max number. Yeah, additional, well, yeah, keeping a sorted list, but then that also means that's the same thing as saying a heap. Are there restrictions on prices that would allow us to use a vector? No. Okay. I think my stomach is going to demand that I take a break before I do 10 minutes of exercise. The timing on my, was not quite right. Alright, well, be right back. Alright, did y'all solve this for me yet? Let's see. Yeah, well, I mean, we could just cycle through the list repeatedly, keeping a copy of the list, asking what the first number is that is less than a given number. But that would require repeatedly copying a list. Well, no, I'm not sure that's what happens if you perform that operation. We would have to ask. If I cycle repeatedly through a list, does that create a new list, or does that merely go back to the beginning and start over? Because actually, in that case, it wouldn't be so expensive. Might as well. All right, let's ask. Suppose I do such and so. Let's see. Suppose I have a lead code problem like this. I can solve it this way. I take the head of a list, I cycle through the list until I find a number less than that head number. I subtract the lesser number from the head number. List. I remove the head of the initial list and perform the same operation with each subsequent element. Can you explain how this works in memory, particularly I'm concerned that this requires copying the list. That would be terribly efficient. The alternative simply is interesting. Alright, I have have some lunch reading now. We can even keep this on screen. Look at this content that the interlocutor and I are providing you with. Look at that content. Yes, your concern is well placed. Yeah, I'm glad to hear it. Alright, I'm gonna start by doing seated warehouse Tai Chi while I read this. Your concern is well placed, and your instinct about list copying is technically correct in general, but not necessarily cause for alarm and racket if we understand how list traversal and structure sharing work. Let's walk through this carefully. Your algorithm in outline. You're doing something like this. Scan X's. Define head, car of X's, rest, CDR X's, /list, X rest, when, that's a convenient optional argument, when less than X head minus head X. We might use that for subsequent problem. We might even just explicitly use this. Then you repeat this with CDR X's and again until the list is empty. Yeah, so for that matter, this would be a /list with an embedded /list, I think. Actually, I'd have to think about this. We'll put that aside. Okay, but the structure, the idea is well represented. Your concern, am I copying the list repeatedly? The answer is no, not unless you do something that forces a copy. What happens in memory per iteration? Let's say X's equals the list containing 9, 4, 5, 3, 6. Then head equals car X's. Okay, fetches the const cells car, no allocation, no mutation, no copy. Rest equals CDR X's, fetches pointer to tail of list. So this all takes place in pointers. Rest fetches pointer to tail of list. Again, no copy. Ragged shares the original list structure. So now you have head equals 9, rest equals the list containing 4, 5, 3, 6, points into original memory. Alright. You run a loop over rest. This constructs a new list of results. Yes, this part allocates, but it only allocates for the result list, not the original input. Alright. Next iteration, CDRXs. When you recurse with CDRXs, you again get a pointer into the existing list. You never copy or mutate the old list. Okay. Rather, you again get a pointer into the existing list. You never copy or mutate the old list. So if you're doing define scan all x's, if null x is null, otherwise const scan x's onto scan all CDRXs, then x's, CDRXs, and CDRXs, etc. are all lightweight pointers to the original list. No copying occurs unless you use append, reverse, or explicitly rebuild a portion of the input. When copying does happen, you'll get copying if you do any of the following. List to vector x's allocates a whole new block. Append x's, y's rebuilds the left spine of x's. Allocates entirely new const cells if we run reverse. Right, storing portions of the list in a vector, boxing required. Okay, and using mutation on a shared spine. Set car, set CDR, but these are rare. Yeah, and that would be scheme. So actually, yeah, we might have a follow-up question here. I'll investigate. Shouldn't take too long after lunch, because one of my ideas has been, what if we put in why don't we ever use mutable lists? Why don't we put mutable lists into the midst, or at the end of lists, and then that would allow us to extend the list from the end. albeit we would only be able to access either from the beginning of the list or specifically that cell, that mutable cell. Let's see. Conclusion. Racket lists are const cell linked lists. Traversal and tail access are pointer operations, not copies. Alright. Not covered in SICP, so far as I'm aware, or not explicitly discussed. I mean, there's not really any discussion of memory in SICP. Unless you explicitly rebuild or consume the list structurally, e.g. with reverse, your memory usage is efficient and copy-free. Your algorithm is structurally sound and does not copy the list per iteration, unless you do something in your loop that forces structural rebuilds. I think we can forego that. Alright, so we got 5 more minutes of exercise. However, right, I'll see if the mutable if the mutable box, as it were. Well, yes, for that matter, why don't we just, well, it wouldn't be a box. Why don't we put, well, yeah, I mean, we could put a box containing a list at the end of a list. Let's see, could you explain the dynamics in play? Box at the end of a list. Define box in place the box at the end of the list of a list, and then place a list extension into the box. The idea being to grant myself access to different list. The box emoji. Oh no. I like this emoji. Oh no. Set up a box at the tail of a list. Suppose you do something like this. Define tail box null. Okay, and now define list start, list 1, 2, 3 tail box. List of 4 elements. I'm not sure that's what you'd want to do. I think it would be more like, well, I could run checks for tailbox instead of running checks for null, but I think instead you'd want, it would just be 1, 2, 3 box null instead of having the tailbox. Maybe I'm misunderstanding how this would work. Well, no, because you're not consing, you're listing, so you'd have a list containing box and null at the end of the list instead of consing where you'd have 1, 2, 3 box null. So I think you would either want to change this list to cons, or you'd want list 1, 2, 3 box null. But anyway, let's see. List start is a list of 4 elements, 1, 2, 3 in a box, not a pointer to the 4th element. It's a boxed value. Okay, the final const cell contains the box as its element, not a pointer to a next const cell. Alright. Then you do set box, tail box, list 1, 2, 4, 5, 6. Now tailbox points to the list 456, but list start still ends with a const whose CDR is empty and whose car is the box, not the new elements. So you have not extended the list, you've just placed a box in it, a container holding a new list, not an inline tail. To actually extend the list dynamically. Yeah, so, but that's so... I'm not I still would be willing to do this, I think. The point is that I would run checks for the box. I mean, really, so this is asking, can I set up an operation where... yeah, but why would I want to do that would be a question. I mean, what benefit would I gain to... Well, I could put multiple boxes in, I guess. I'm not sure. Let me think here. To actually extend the list dynamically, you need to place a mutable cell in the CDR position, which scheme style const cells don't let you do directly unless you're using mutation. Yeah, and we don't want to do that with Racket for the most part, but then to build a list x's 1, 2, 3 box and later do set box list 4, 5, 6 and thereby get. Then you're emulating set CDR exclaim with a box. Alright, correct pattern, fake a mutable tail pointer. Here's how you actually do it. Define tail box, null, okay. Define last const, last pair x's. Help her to get to the final const cell. Is that actually a command? Huh. Set CDR, last const tail box. So this would be, again, scheme rather than Racket. Because in Racket it's set MCDR, if I recall correctly. Or maybe MCDR set, something like that. Let's see. The original list is 1, 2, 3 box. The CDR of the last const cell is the box. Box's contents is now list 4, 5, 6. Yeah, otherwise not a proper list. Okay. So define flat walk list, and this is saying, yeah, we do a box check. I'm not sure what the pair check is going to be for. Const carve the list onto. Let me see. Well, so this would make it behave as if we were passing through a list. The box question mark flat walk unbox list. Okay. This creates improper lists, i.e. lists that include dotted pairs or non-consts in CDR positions. Racket functions like length, for list, map, etc. will fail or produce garbage. It is a valid structure but not compatible with standard list functions. You're now in mutable const style territory. That's the kind of program usually reserved for splice once constructions in a trusted context. Like a poor man's queue. If you want to manually simulate coroutines, continuations, or pipelines, you are writing a tree zipper. So the point is that yeah, you set in the box detection, and then it will, any operation will behave as if, or your operation will behave as if it's a list. That lets you for loop over these box-tailed lists. Oh no. You can use boxes to inject dynamic tails, but you must write your own walker, use the discipline, and avoid pretending that these are proper lists once you've gone off the rails. Alright. Well, I'm gonna go eat lunch, and then when I return, it will be more studying of code. See you soon. Have a good one. Hey, what am I doing? I was exercising. Now I'm going to go eat lunch. Never mind. Okay, see you soon. What is that? Is that off-putting? Yeah, maybe. Anyway, see you soon.